So chapter 2, this is the chemistry of biology. So it's basically from your Chem 3 class. Okay. All right. So atoms, bonds, molecules, matter. All matter that occupies space and has mass, matter is composed of atoms. So anything that has space and occupies mass is considered matter. And matter is made up of atoms. Atom is the smallest or simplest form of matter that's not divisible into simpler substances. You can't divide an atom into smaller things. Okay? Atom is the smallest particle that makes up matter. Now, what makes up an atom is protons, neutrons, and electrons. Protons have a positive charge. Neutrons have a neutral charge. Electrons have a negative charge. And they're all subatomic particles. Okay, so basically you have a nucleus inside an atom, and you have these electrons spinning around it in these orbits that come around this electron. So if you think about the center of an atom is the nucleus, and you think about the entire size of the atom, it's like Qualcomm Stadium or a football stadium down in San Diego. The atom would be a P. The space electrons occupy would be the entire stadium. So the nucleus is a very, very tiny amount when you're looking at it. And in the nucleus, you have protons and you have neutrons. And spinning around it in these orbitals, you have what's called electrons. And these spin around to what's called shells or energy levels. Okay? So what makes up the mass of an atom is your protons and neutrons. The number of protons. The number of protons determine the name of the element, what the element is. If it has 1 proton, it's hydrogen. If it has 6 protons, it's carbon. And that's just on a periodic table. So the number of protons determine your element. Okay. All atoms share the same fundamental structures, protons and neutrons in the center, what's called the nucleus, and the electrons around them. An element is a pure substance, characteristic number of protons, neutrons, and electrons, and predictable chemical behaviors. Okay. The electrons determine the chemical behavior, how they react. So here you have an atom of hydrogen. Hydrogen has 1 proton. So you see in the center, there's 1 proton. Electrons form a cloud of orbits around it, called orbitals. Okay. So in carbon, you have 6, so protons equals 6. So inside the nucleus here, you can see 6 protons and you can see 6 neutrons. That gives it the stability of the nucleus inside. And you see the orbitals where these electrons fly around, where these electrons exist in these orbital clouds or energy levels. Different shells. Okay. This is a major elements that are found in living organisms. There's 4 major ones: carbon, hydrogen, oxygen, and nitrogen. Those are the 4 major ones. There's some other minor ones, which is the rest of these here. You'll see what they are. Like you see calcium, the atomic symbol for calcium is Ca, the atomic number is 20, okay? The atomic mass is 40, and the ionized form is calcium plus 2. It gives off 2 electrons to leave a positive charge. If you remember your periodic table, that line that kind of goes diagonal on the right-hand side of it, to the left of that is metals, which is positive charge ions. To the right of that is non-metals, which are negatively charged ions. Like chlorine. Chlorine would have a negative charge because it gains an electron. But the atomic number tells you the number of protons. So anything you look at, if it has 29 protons, it's going to be copper. If it has 6 protons, it's going to be carbon. That's your atomic number. Now the number of protons cannot vary for the element. The number of neutrons can. That's where you get like carbon-14, which is radioactive. We use that in radioactive dating and things like that. Okay. We'll get to that in just a second here. Okay. So when you're naming a compound, the first letter is always capitalized. If there's a second letter, it's always lowercase. So we have magnesium. Magnesium is Mg, so M is capitalized, G is lowercase. Sodium is Na, because it goes by the Latin name. N is always capitalized, A is lowercase. There's only one letter, like oxygen, it's always capitalized. Okay. That lets you tell the difference between certain elements and different compounds. Like CO is cobalt. CO, capital O, is carbon monoxide. Okay, so whenever you have an element, the first one is always capitalized, the second one is always lowercase. That allows you to distinguish it between names of different compounds. Okay. So you have the atomic number, which is your number of protons. Then you have your atomic mass. The atomic mass is the weight of the element, which is the weight or the average mass for the isotopes of that element. Isotopes, okay, are the same number of protons, but different number of neutrons. Okay. Say we have carbon. Let's take carbon as an example. Carbon, and this is carbon 12, is 6 protons, 6 neutrons. Carbon 13 is also 6 protons, 7 neutrons. Carbon 14, 6 protons, 8 neutrons. Okay. So you notice the protons always stay the same. That's what determines your element. If the neutrons vary, it just makes it different mass, because neutrons weigh 1 unit, atomic mass unit. Okay. So C14, which is very small, found in nature, but it is radioactive. We use that to trace or date certain elements that are found that have been living in the past. We use that for carbon dating. Okay. So what we talked about is atomic number is a number of protons. The mass number is the protons plus neutrons. Isotope is the same element. Same element means the same number of protons, different number of neutrons. Okay. So isotopes are the same element, except they have the same number of protons, but a different number of neutrons, so they're a different mass. The atomic weight is the average mass of all the isotopes forms. So we take the isotopes like carbon 10, carbon 12, carbon 13, carbon 14. We figure out their percentage in nature. We assign each one to their value, add those together, and that gives us our atomic mass, or molecular weight. Okay. That's the mass of the element in nature. That's where the number comes from, the periodic table. That's why it's not exactly an integer, because it's a mass average. Electron orbitals are volumes of space around the atomic nucleus where electrons are likely to be found. So you can't see electrons. Okay, if you shine a light on an electron, the electron moves because the electron weighs more than the light source. Okay, so it's not going to be where you found it. You can't find it. It exists in these areas. We talk about probability of finding electrons in a certain area. That's what we have. Okay, so here's our electron flying around our car shell on an orbital around our nucleus. That's hydrogen because there's 1 proton. Carbon has 6 protons. Okay. It has electrons flying around it and 2 energy levels, 2 shells. Okay. So you can see the shells filling up here. Remember your SPDF orbitals from Chem 3? This is what that is. These are the different energy levels that the electrons can occupy. Biologically important ones, I said carbon, the 4 basic ones that make up most: carbon, oxygen, carbon, hydrogen, oxygen, nitrogen. Okay. The other ones are somewhat make up different masses in there, but those are the 4 main elements. Okay. So you have hydrogen. Okay. You have sodium, Na with atomic number of 11. You have potassium, which is 19, calcium, magnesium, carbon, nitrogen, oxygen, chlorine, sulfur, and phosphorus. You'll see all the different number of protons. That number there, phosphorus, says 15, has 15 protons. Okay, calcium has 20 protons. So the number on your periodic table determines the number of protons that you have. Okay, so first check. If two atoms have the same number of protons and electrons, but different number of neutrons, they would be what? Different elements, isotopes of the same elements, ions of the same element, or orbitals of the same element. Which would they be?
Isotopes.
Isotopes, perfect. They'd be B. Isotopes of the same element. If they had different number of ions, the ions would be different number of electrons because they control your charge. But that would be B, isotopes of the same element. Same number of protons, different number of neutrons. Right. Now we're going into bonding and how these interact with each other. Any questions so far?
No.
Perfect.
No, thank you.
All right, no problem. Good. I'm glad it's all working because like I said, school's having lots of trouble with the internet, so I'm glad it's working now. So a molecule is a chemical substance that results from combination of two or more atoms. So when two or more atoms combine, you form a molecule. Examples of a molecule are water, H2O, 2 hydrogens, 1 oxygen. Carbon dioxide, 1 carbon, 2 oxygens. So anytime different elements combine, when there's 2 or more, that is a molecule. Compounds. Okay. Molecules that are combined are a combination of 2 or more different elements. Okay. So it forms a compound. So the molecule is 2 or more atoms. Compound is 2 or more elements. Okay. Like a molecule could be oxygen, which could be O2. Okay, that's not a compound, it's the same element. Cl2, chlorine gas. Okay. Those are 2 of the same atoms. When they're different atoms, they're formed compounds. Okay. We can have a mass or a weight of that compound. We sum up the electronic masses of atoms a molecule contain. Does it contain in the molecule? So like the formula of water, H2O. There's 2 hydrogens, there's 1 oxygen. If you look at the periodic table, hydrogen weighs roughly 1. Oxygen weighs 16 or 15.999. Okay, so we round those up. So the total weight for water is going to be 2 because there's 2 hydrogens, each one has 1, and 16. So it's 18 is its molecular weight. We just use it the same way we do everything else. CO2, carbon has 1 carbon, 2 oxygens. Each carbon is 12. Each oxygen is 16. So it's 32, that is 44. And then look at the weight of 44. 1 carbon, 2 oxygens. Every carbon is 12, every oxygen is 16. And you get those numbers from the periodic table. They're right on the periodic table. All right, so chemical bonds. Here's my. Pop it up there. Okay. In chemical bonds, there's 2 or more atoms. They share, donate, or accept electrons to form molecules or compounds. You have 3 types of bonds, basically. You have covalent bonds, you have ionic bonds, and you have hydrogen bonding. Those are very important in microbiology. Those 3 types of bonds we're going to have. Each one is different. Covalent bonds. In the covalent bond, electrons are shared between the atoms. So electrons don't transfer, but they're shared between them. And in a covalent bond, you can have either polar or non-polar covalent bonds. So they can share differently. If we have a covalent bond between hydrogen and fluorine. Okay. Remember the term electronegativity from chemistry? It's how much something wants an electron. Fluorine is the most electronegative element that we have, so it wants electrons. So it pulls the negative charge this way. So this is a little bit minus, this is a little bit plus. Because remember, electrons are negative. If we're pulling them towards something, it becomes more negative. We're taking them away from something, it becomes more positive. So that's a polar covalent bond. Okay. If the compounds involved in the bond attract electrons the same, like 2 chlorine atoms, Cl bonds to Cl. That's a non-polar bond. 1 chlorine is not going to put electrons more towards itself than the other. Okay, those are both covalent bonds. One is a polar covalent bond, one is a non-polar covalent bond. In the nonpolar bonds, there's equal sharing. In the polar covalent bonds, there's unequal sharing. Okay. Okay, so in our covalent bonds, okay, we have our two atoms coming together and they share those electrons right between them. There's equal sharing between them. Just like on the bottom here, you can see the next one here. You have these two electrons going to be shared, and that's going to form what's called a double bond. Okay. So this is a single bond right here. This is a double bond because there's 4 electrons shared. If there were 6 electrons shared, it would be a triple bond. So hydrogen forms H2, which is a shared, they each share the 1 electron between the two. Okay? And it takes 2 electrons to make up a bond. So 2 electrons make a single bond, 4 make a double bond, 6 make a triple bond. Right? So there's 2 electrons in each bond. Okay? So that's hydrogen. And over here we have nitrogen, oxygen. O2, oxygen, 4 electrons between them. That is a double bond. So what's written is oxygen, double bond to oxygen. Okay, remember Lewis structures? Carbon can share. Carbon has 4 what's called valence electrons, so it can make 4 bonds. So it can bond to hydrogen 4 times, and you have methane gas, which is CH4. So we're talking about polarity. We talk about water. Water has covalent bonds, but the bonds are unequal share. Oxygen has a higher electronegativity than hydrogen. So oxygen pulls electrons towards itself. When it pulls electrons towards itself, it gives it a negative charge and leaves a positive charge behind on each hydrogen. This is what's going to allow for hydrogen bonding. Okay, so we have covalent bonds we talked about. Then we have ionic bonds. And then we'll talk about hydrogen bonds after that, which just have water. So ionic bonds, okay? 1 or more electrons is removed and another forming a positively charged cation and anion. And these electrons are transferred from one element to another. So covalent bonds are shared. Ionic bonds are a transfer. In other words, one electron physically moves from one element to the other, and that forms charges, and opposite charges attract. So sodium has 1 valence electron. Chlorine has what's called 7 valence electrons. So this electron moves into here, and you end up with Na, and now you've lost an electron, so it's a positive charge, and CO minus has gained electrons, so it's a negative charge. Okay, so you actually transferred an electron. So the positive charge attracts negative charge, and it forms a bond. This is an ionic bond. And that's what forms your crystals, salt crystals. Okay. So covalent bonds, they share, ionic bonds transfer. And that transfer produces charges. Cations are positive, anions are negative. And they attract one another. Okay, so here's your ionic bond. Your electron physically moves to this other one. That leaves this a positive, that leaves this a negative, and then you have an attraction. Because opposite charges attract. And that's what forms crystals. These are salt crystals here. Okay, so you can see the crystals being formed. Because it forms this crystalline layer, positive, negative, positive. Because you got to remember, if you got a positive charge, think of a cube. You got a negative charge all around it, and then one above, one below. And it's going to form a crystal. Then you have a negative charge that has a positive charge. So each one of these atoms, okay, has 6 other opposite charges around it. Just like it looks like a dice. Okay, ionic bonds. Ionic bonds are plus and minus charges. So plus and minus charges, water is polar. It just shows you water has plus and negative charges also. So water can suspend the plus and minus charges of the salt, the sodium chloride, into solution. That's why salt is dissolved in water, because it has positive and negative charges. That's why oil is not dissolved in water. It has no, it's all covalent, has no positive and negative, no polarity, no positive and negative charges. So it won't dissolve in water. So something has to have positive and negative charges so it can dissolve in water. It has to be polar. All right, so you talked about covalent bonds, which is sharing, ionic bonds, which are transferring. Now we got hydrogen bonds. Hydrogen bonds is the interaction between hydrogen and other molecules where there's been a charge. In other words, here's our water molecule. Okay, oxygen is negative, hydrogen positive, because oxygen is more electronegative. So it pulls electrons towards it. So the positive end of one molecule will interact with the negative end of the other. Okay, positive and negative charges attract, positive and negative charges, and this holds water together. Right? That's why if you throw a flat rock on top of water, it will skip, because water has force holding it together. The rock will hit and skip across there because you have hydrogen bonding. Okay? If there was no hydrogen bonding, a rock would sink. Try filling a lake with gasoline. I mean, you're not going to actually do that, but gasoline has no hydrogen bonding. It's all covalent. Okay? There's no hydrogen bond there. You throw the rock across there, it sinks. There's nothing that's going to make it skip. Okay?
Would the gasoline just eventually like dissolve into the like the earth? Like, because it has nothing holding it.
Whereas an environmental hazard. That's why oil spills are so bad, because they don't go anywhere. They can't dissolve in water because there's no polarity.
Okay, yeah, it just stays there. It just stays on top of the water.
Well, it depends on the density of what type of gasoline you're using, but if it's more dense than water, it sinks. If it's less dense than water, it floats. The problem with gasoline, like octane, it's less dense than water, so it floats, and it causes a problem. If we had oil spills in the ocean and the oil was more dense than water, it would sink to the bottom and cause no problem. But it doesn't. It's less dense than water, so it floats on top of the water. Okay? And it won't be absorbed in because it is nonpolar. Okay, but it doesn't have this strong bond effect. You ever notice those little bugs that walk across water? They do that because it's hydrogen bonding. That water is adhesive and forms a layer around it. Okay, like I said, if you take a cup of gasoline and put the bug on top of the gasoline, that same bug, he'll sink right down the bottom. Because there's no hydrogen bonding, there's no cohesive force across that. You ever wax your car and then put water on? What happens? What happens to the water? It forms a bead, right? Yeah, you take your car, you pour water on it, it forms these little beads. Okay, because water bubbles up. It's adhering to itself, but it's not adhering to the surface of the car or the hood or the trunk, whatever you polished or waxed. Okay, so it comes up and the hydrogen bonding holds it together. Okay, when you have a droplet of water drops as a sphere, right? The droplets of water come down. Okay, the hydrogen bonding is what's holding all this together. When you pour gasoline, you don't get droplets. You just get a stream because there's nothing to hold it together. There's no hydrogen bonding. Is that making sense?
Yeah, that's really cool.
Okay, yeah, it's really slick how it works out. It just, hydrogen bonding is an amazing principle, and it's phenomenal what it does. So I mean, and they're not as strong as ionic or covalent bonds. Ionic and covalent bonds are very strong. Hydrogen bonds are not that strong, but they're strong enough to hold them together for certain purposes. Okay, and that's what's really important in microbiology. What we're going to do with water with hydrogen bonding. So here's your hydrogen bond. Again, it occurs with, it doesn't have to be hydrogen and oxygen, it can be hydrogen and fluorine, hydrogen and nitrogen. It's still going to have a hydrogen bond. Any molecule that's more electronegative than hydrogen is going to pull electrons towards it. So there could be oxygen and hydrogen, it could be nitrogen and hydrogen, it's an H. It could be fluorine and hydrogen, and all those are going to pull electrons this way. So these are all be negative, these are all going to be positive. And because of that, you'll get this attraction. This is a hydrogen bond. So hydrogen bonds are what's called intramolecular. Covalent and ionic bonds are intermolecular, within the molecule. Okay? This is your covalent or ionic bond. This is your hydrogen bond between molecules. So covalent and ionic bonds are in the molecule itself, like the sodium and chloride held together by it. Okay? The actual hydrogen bond is between the molecules that are already bonded. So hydrogen bonding is what's called intramolecular. Covalent and ionic are intermolecular, within the molecule. Okay. See if you understand this one. Molecules where atoms share electrons contain what types of bonds? When they share an electron, is it covalent, ionic, or hydrogen?
Covalent.
Covalent. Got it. Perfect. Okay, oxidation reduction reactions are important in the human body. Okay. Energy exchange in cells is a result of the movement of electrons from one molecule to another. Okay, so it's supplying energy to our bacteria and things like that. They undergo oxidation reduction reactions. Oxidation is the loss of an electron. Reduction is the gain of electrons. But you got to think about it. And it makes sense when you think about it is electrons are negative. So when you lose an electron, it becomes more positive. That's oxidation. Okay? Reduction means reducing the number. So when you gain electrons, you're adding negative charges. You're making that number smaller. Okay? So that's oxidation reaction. And they're called redox reactions. One does not occur without the other. If something's being oxidized, something else has to be reduced. They do not occur independently of one another.
So,
Go ahead.
oh, sorry. So you said the oxidation, the loss of electron makes it more positive, right?
Correct. Makes the number bigger. Reduction is the reducing or the lowering of the number because you're adding negative charges to it. So reducing agents and that causes reduction gives an electron off. Okay, so a reducing agent causes reduction. Okay? This has been reduced because it's added an electron to it. Oxidizing agents accept electrons, okay? So it decreases the number of electrons. You decrease the number of electrons, you have oxidation. Okay? So this is real quick overview of those. If there's any questions, let me know because I've taught Chem 3 before and I'll be more than happy to help with any of that. But in a chemical reaction, reactants are on the left, products are on the right. Reactants that we start off with, products are what we end up with. So these are our reactants right here, sulfur and oxygen. Our product is sulfur dioxide. Okay, this is what's called a synthesis reaction. Synthesis means we made something. We're produced SO2. Okay, and they produce a new molecule. Decomposition reaction means we've broken something down. Hydrogen peroxide went to water and oxygen gas. Hydrogen peroxide breaks down real easily to water and oxygen. That's why peroxide bottles are what color in the store. They're brown because light accelerates this reaction. So if you take hydrogen peroxide, put it in a sealed bottle where it has no way of gas escaping, expose it to light, you've got a bomb. You're producing gas in a sealed container and it's going to explode. Okay, so that's why hydrogen peroxide bottles are brown. The light doesn't penetrate it, so you don't get that reaction occurring. But this is a decomposition. One thing breaks into two or more products. This is a synthesis. Two or more things form one thing. So synthesis, you're creating something new. Decomposition, you're breaking something down. And then you've got exchange reactions, where one thing's being exchanged for the other. Here we have HCl plus NaOH, and we're going to form sodium chloride and water. I'll put water as HOH, okay? Because this hydrogen now combines with this OH, and that forms water. This sodium combines with this chlorine, and that forms NaCl. So it's an exchange reaction. You're exchanging the positive parts to combine with the negative parts of the other one. Okay, because opposites attract. So this is H plus, Cl minus. This is Na plus, OH minus. So here's the positive, here's the negative. Here's a positive, here's a negative, here's a positive. Those are what's combined. Okay, so those are what's called an exchange reaction. Okay, so a mixture, we have solutions. We use solutions all the time. Bacteria live in solutions. Most bacteria and viruses die on a dry surface. Okay, even the AIDS virus, expose it to a dry surface, it's going to die. Okay, they need a solution. They need a medium to exist in. A solution, by definition, is a mixture of one or more substances. One of the substances is a solute, and one of the substances is a solvent. Okay, the solutes are the little amounts. The solvent is the big amount. If you've got a sore throat, doctor tells you to rinse with warm salt water, right? You take water, you put salt in it. Okay, that's the water is the solvent. The salt, sodium chloride, are these solutes. So solutes are what you add to the solvent. Solutes are the smaller amount. The solvent is the bigger amount. Okay? And if you add sodium chloride, it'll dissolve. If you add calcium chloride, it'll dissolve. If you have magnesium fluoride, it's going to dissolve. Okay? As long as it's polar, ionic, it's going to dissolve in water because water is polar. Terms we use with bacteria. We're going to use that when we have molecules of different things. There's certain areas of bacteria, and some are going to be hydrophilic, some are going to be hydrophobic. Hydrophilic means water loving. It's philic is Greek for love. Phobic is Greek for fear. Okay, so hydrophilic means water loving. It dissolves in water. It loves water. Hydrophobic means afraid of water. It repels water, like our oils. Okay, it's a non-polar substance. So we'll use the terms hydrophilic and hydrophobic a lot. Okay, because different parts of the bacterial cell membrane, some are going to be hydrophobic, some are going to be hydrophilic, and that's going to offer different properties to exist. Amphipathic are, they have both hydrophilic and hydrophobic properties. You can have a section of membrane or a section of protein in your body where a certain part is hydrophobic and other parts are hydrophilic, and that determines the shape of the molecule. And determining shape determines biological activity. So hydrophilic is water loving, hydrophobic is water hating or water fearing. Amphipathic is both. They have both hydrophobic and hydrophilic portions to that compound.
Can you give an example of something that's how do you say that?
Amphipathic?
Amphipathic?
Amphipathic is like insulin. Insulin is a folded protein. It has areas where it comes out with, say we come out with, I'm trying to think of the compound here. That puts out its phosphate bases here. Let's draw a protein here. And this would be, trying to put a sodium, these are all filled. And inside of here, you'd have like cholesterol. Cholesterol molecules would come in here and they would group together. And cholesterol is hydrophobic, I'm sorry. Whereas salt, sodium, magnesium, whatever's on the end here of your membrane, these are hydrophilic. So water will be attracted here. So what happens in a water environment is all these are exposed to water, and then where there's like cholesterol booked in your membrane, those are hydrophobic. So they group into one group and they fold this membrane to get away from the water. So portions of it are hydrophobic, portions of it are hydrophilic. Does that make sense?
Thank you, yes.
Okay, and that determines the shape of the different proteins. Well, I mean, one part of the molecule cannot be hydrophilic. It has to be different portions. It's either hydrophobic or hydrophilic, but it can be part of the same membrane. Does that make sense that way?
Yeah, I think so. Yeah.
Okay. I mean, one part can't be both.
Yeah,
Okay,
one part can't be both. You have both, but they're within the same realm, the same membrane. Yeah.
Yes, you got it.
Yeah, that makes sense.
Okay, perfect. That's exactly what happens. Okay, how pH scale and acidity. Ionization of water produces H plus ions. H plus ions are the measurement of an acid. Okay, water breaks into H plus and OH minus. Okay, that's your hydroxyl ion, that's your hydrogen ion. pH ranges from 0 to 14. That lets you know the concentration of hydrogen ions. pH, by definition, is equal minus the log of the H plus concentration. So the lower the number, the higher the H plus, the lower the pH. It's a minus log of it. So the more acidic it is, the more H plus ions are in solution, the lower the pH is going to be. Okay, so pH of 0 is hydrochloric acid, 1 molar, very strong acid. 0.1 molar hydrochloric acid is pH of 1. The pH scale goes by log, so it's log to the base 10. So if you go from 1 to 2, it's a 10 times increase. If you go from 1 to 3, it's 100 times increase. If I go from 1 to 4, it's 1,000 times increase in strength, or decrease of it, which we're going. Okay? So every integer is a factor of 10. 10, 100, 1,000, 10,000, 100,000, etc. Okay? So if you look at hydrochloric acid is 0.1 molar hydrochloric acid, pH of 1. Look at a pH of 2 is lemon juice, which is really close to hydrochloric acid. So I just want to take the strength. Coca-Cola, Pepsi has a pH of roughly 2. Okay. It will dissolve your teeth, literally. You want to do a science experiment with your child, take a bottle of Pepsi, take your child's baby teeth that come out, put in Pepsi, see how long it lasts. Put in Coke, see how long it lasts. Pour Coke on your table. It'll eat right through the varnish and eat right through the wood. Okay. It's extremely strong acid. Okay. If you got bolts on your car that you can't get off, pour Coca-Cola on it. It'll dissolve the corrosion away. Works really good. Just doesn't work really good on your stomach. So extremely high acids have a pH of 1, extremely strong acids. Extremely strong bases have a pH of 14, the exact opposite scale. This is an OH concentration. Now, OH concentration can be just as deadly as the H plus concentration. Okay? It still is very corrosive. Okay? It will dissolve. If you ever see Fight Club, Fight Club is a great movie. It's the chemistry behind it is phenomenal. When they burn the guy's hand, they make the tattoo. They put on base. They put hydroxide, some hydroxide. And that's what it'll do, it'll burn right through your skin because it has a high OH concentration. So both ends of the spectrum are extremely dangerous to the human body. The middle is 7. 7 is distilled water, pH is 7. So that's how the pH scale. It's increments of 10. The lower the pH, the stronger the acid. The higher the pH, the weaker the acid, the stronger the base. So there's your logarithm scales, 1 to 14. You can see every increase is by a 10. 10 to the 0, 10 to the 1, 10 to the 2, negative, etc. Everything increases or decreases by a factor of 10. So if solution A has a pH equal to 2. Solution B has a pH equal to 4. Which statement is true? Solution A has 2 times more hydrogen ions than solution B. Solution B has 2 times more H plus ions than solution A. Solution A has 10 times more H plus ions than solution B. Or D, solution B has 10 times more H plus ions than solution A. Or E, solution A has 100 times more H plus than solution B. Which one would it be? Remember, it's increasing by a factor of 2. So if you increase by a factor of 1, that's 10. Increase by a factor of 2, that's 100. So solution A has 100 times. This is 2, this is 4. The difference of a factor of 2, which is every factor is a factor of 10. Okay, every integer. So from 2 to 3, 3 to 4, So it's 100 times more H plus ions than solution B does. Okay. Organic chemistry. Organic chemistry is a chemistry of carbon. If you ever get a chance to take organic chemistry, I loved it. I love teaching it. That's my favorite class to teach, organic chemistry. It's all poisons and explosives. That's what organic chemistry does. There's all the things that you can do with all kinds of compounds. But it's compounds and they're carbon hydrogen compounds, okay, called hydrocarbons. So carbon is a fundamental element of life. So all life is based upon carbon, because carbon can have multiple different types of bonds to it. Carbon can have single bonds. It can have single bonds like carbon and hydrogen. It can have double bonds like carbon and oxygen. It can have triple bonds like carbon and nitrogen, like cyanide. It's very versatile because a carbon has 4 what's called valence electrons. So carbons can make up to 4 bonds around it. So it can form single bonds, double bonds, triple bonds. It can form linear compounds. Okay? It can be branch compounds, or it can be ring compounds. Okay, so carbon, if you look at carbon, every corner is a carbon. Okay, that's octane. That's gasoline. Okay, every corner, every dot, every space there's a bend is a carbon atom, and then a hydrogen to make it have 4. So there'd be 3 hydrogen here, 2 here, etc. Okay, it can be branched. You have different branches on it, and that will still form organic compounds. Or it can be ring molecules. It can form different ring structures. Okay. When we bleach teeth, okay, teeth stain because of coffee, red wine, things like that in excess. Okay, these ring structures form inside the tooth. The ring structure stops the light from passing through it, and it looks darker. That's what makes dark teeth. So when the dentist bleaches teeth, I just break this bond right here and opens up into a linear compound. Light passes through, the teeth look white again. That's what bleaching is all about when you bleach teeth. You're not taking the stain out, you're not doing anything. All you're doing is breaking the ring structure of carbon and making it into linear so light can pass through now. That's all that's involved in it. It's really cool how people thought this stuff up. Okay, so here's carbon in its action. It could be carbon hydrogen, it could be single bonds, double bonds, single bonds of nitrogen, carbon-carbon bonds, carbon-carbon double bonds, carbon-nitrogen triple bonds. It could be carbon-carbon triple bonds. Ethylene, what you use in welding, is carbon, triple bonded carbon, bonded hydrogen. Okay. That's an acetylene torch. That's acetylene. Okay. Carbon, cyanide. Cyanide is a toxin. That's what we use in the gas chambers. Okay, we take a bowl, you put not the patient, the convicted criminal, hopefully the right convicted criminal, put him in the airtight cell with oxygen in there. We have a bottle of water, a bottle of acid, a bottle of water underneath it, and we dip hydrogen cyanide in it. The cyanide is released into the air, and it forms this carbon triple bonded to nitrogen, which is CN minus. Now, what's unique about cyanide is cyanide bonds to hemoglobin, and it bonds irreversibly. It bonds so oxygen can't bond anymore. So that means oxygen can't bind to your red blood cells. Oxygen can't get to your cells. Cyanide does. Cyanide bonds to your blood cell and sticks to it. Has a higher affinity for hemoglobin than oxygen does. So therefore bonds to it, goes through the circulation. Oxygen can't be perfused through the body. Patient asphyxiates. That's how cyanide poisoning works. Okay, so it's got a lot stronger bond for hemoglobin than oxygen does, with that triple bond to nitrogen.
Is it hemoglobin like your blood, so it bonds to your blood?
No, not to your blood. Hemoglobin is your red blood cell has hemoglobin in it. Okay, and it circulates through the body into your lungs. The cyanide goes into the lungs, and oxygen goes into the lungs. The cyanide is going to compete with oxygen to bind to the hemoglobin in your red blood cell, so it can carry the rest of your body. The cyanide is going to win out. the cyanide wants it stronger. The cyanide will displace oxygen, put itself there, and then not move. Okay? So oxygen, you're going to run out of spots for oxygen to bind to, so oxygen can't get to the cells of your body. Only cyanide stays bonded to the hemoglobin in the red blood cells, not in the bone. Okay? Your red blood cells are formed in the bone, but the circulation, we go to the lungs, that's where it absorbs the oxygen from, not from the bone. Did that answer your question, Megan?
Yes, it's very interesting. Yes.
Yeah, it's really, yeah, I mean, look at carbon monoxide poisoning from a car. Okay, you go in the garage, same principle, except it's not as strong. You have oxygen, if you're in a sealed garage, turn your car on for a suicide attempt, okay? You have oxygen in the air, and then you have carbon monoxide. Remember, we talked, if hydrocarbons burn, okay? You burn a hydrocarbon like propane, C3H8, plus oxygen goes to CO2 and water. Okay, that's what happens when we burn a hydrocarbon. Now, automobile engines are the same, but they're not as efficient. So they're very inefficient. So they burn carbon monoxide as a product, okay, and by using of oxygen. So carbon monoxide comes out from the fume from the exhaust. Okay, now you're breathing in oxygen and carbon dioxide. Carbon dioxide has a stronger affinity for the red blood cells, just like cyanide did. So carbon monoxide binds to your red blood cells at the hemoglobin instead of oxygen. So basically, you suffocate to death. Now, what's the treatment for carbon monoxide poisoning? Just put them back outside. Open the garage door. That's it. Eventually, the carbon monoxide comes off the red blood cells. Oxygen comes back on because you relieve the source of it, and it's reversible. And so that people breathe outside. Cyanide is not reversible. Cyanide binds to it and it stays on there. You can't just bring out a gas chamber and reprovide. Now, to a certain extent, carbon monoxide, once the body is dead, then it's dead from it. Okay, it's not going to reverse it. But you can reverse it while you're still alive just by bringing the outside exposed into just oxygen. But carbon can be linear, it could be branched, or it form these ring structures like it does inside of teeth. Okay? Glucose is a 6-membered ring structure of carbon. That's the energy that most of the body feeds on. Okay. Organic chemistry, we have different functional groups. It's groups that attach to carbon. Whenever you see the term R, or it's ROH or ROR, whatever it is, R just means a carbon group. That's all it means. Could be CH3OH, could be CH3CH2OH. Okay. Okay. This R group is just a hydrocarbon, just a group of carbon. That's all it is. So don't get confused with the R groups. And these are alcohols. When you see something ending in OH, that is an alcohol. Alcohols are found in carbohydrates, they're found in many different groups. But OH means an alcohol. This is methanol. This is ethanol. Okay? This is the one that makes up your vodka. This makes up your drinks. That's what you get drunk off of. Okay, that's vodka right there. That's methanol. Okay, when ethanol was prohibited in the United States during Prohibition, okay, people couldn't get ethanol. They could get methanol. Now, methanol is a poison. Okay, it's wood alcohol. I mean, ethanol is a poison too. That's why it gives you the effects it does in your body. But you can body can handle certain that. The methanol is wood alcohol. It's a poison. They use this instead of ethanol during Prohibition because people had to drink. And one of the effects of methanol is it makes you go blind. So people would drink enough of it until their vision got blurry. Then they go to the bathroom and throw it up. Okay. You ever hear the expression, keep doing that, you go blind? That's where it came from. Okay. Is this methanol? Is methanol poison? Okay. You got to be really desperate to drink if you're playing that kind of game with your vision and the rest of your body. Okay. But it's just one carbon difference. So anytime you see an R group, if there's an OH to it, that is an alcohol. It's called a hydroxyl group. When you have a COOH, this here, that's a carboxylic acid group. Okay, those are your fatty acids. That's what forms your triglycerides in your body. things like that. We'll show you how that works with in just a second here too. Okay. When you have a nitrogen with hydrogen, that's an amine group. Those are in your proteins, your nucleic acids, your RNA, your DNA. Those are all based on that for your nitrogen groups in there. Okay. All amino acids have an NH2 group on them. When we talk about amino acids, you'll see the exact same thing over and over. Only one part is going to be different. Okay. An RCOOR instead of an OH like carboxylic acid. If this was an H, it'd be a carboxylic acid. If it's an R, it's an ester. Okay, and esters are forming your lipids and your fats in your body. So you have sulfur hydro groups, which is an SH group attached. Now, SH groups form bonds inside the body. They can form disulfide bridges, which is shaping your proteins as it occurs. Okay, those are some different amino acids and proteins. That's a sulfur hydro group. You can have COH group. That's an aldehyde. Okay. Aldehydes are in your sugars that you consume. Okay. When you have another R group with C double bond O, that is a ketone. That's what your body produces. That's what you spill out when you're diabetic. You have ketone bodies that are produced. That's what you're looking for in your sugar when they take your urine. Okay. So we have aldehydes, we have ketones, and we have phosphate groups. These are extremely important, these phosphate groups. Okay. These are what determine ATP. That's what makes ADP into ATP. We add a phosphate group. So we go from adenosine diphosphate to adenosine triphosphate. Adenosine triphosphate is the energy in your body. That's how we store energy. We use ATP in the body. And it's DNA, RNA, all of those are using this phosphate groups. Okay, DNA and RNA have a sugar phosphate backbone that support it, and all the stuff mitochondria produce in your body are ATP. Okay, those are your different, some of the different functional macromolecules. Macro means large, micro means small. So macromolecules are large molecules that we live on, that are used for survival. Biochemicals are organic compounds produced by living things. Macromolecules are large compounds assembled from smaller units. A monomer is a small unit, that's what gets repeated. A polymer is a chain of monomers. So like if we have glucose, glucose is a 6-carbon ring and then bonds to another glucose. Okay, now we have 2 units, bonds to another glucose. Then we have 3 units. Okay, so the monomer is just a single unit. The polymer is the chain that starts when they start to bind together. We have 4 biological macromolecules in our body. We have carbohydrates, we have lipids, we have proteins, we have nucleic acid. We think of the 4 biological macromolecules. Okay, so you have carbohydrates, okay, and you have lipids here. Carbohydrates make up your monosaccharides, which are your small sugar units. And then these combine together to make up disaccharides. Disaccharides are 2 saccharides, 2 monosaccharides put together. So monosaccharides are glucose, fructose. Okay. Disaccharides is your maltose, like malt beer or malt sugar. Those are 2 glucose molecules. Lactose, your milk sugar, because it is glucose and galactose bonded together. Sucrose is glucose and fructose bonded together. Okay. So those make up your carbohydrates. And then also have polysaccharides, which are large chains, more than 1 or 2, or hundreds of thousands, like starches or cellulose or glycogen. Okay. They're used in the cell wall, and used for food storage for energy. Those are long chains of monosaccharides. Okay. And we have glycerides. Okay. They form from glycerol and fatty acids with a dehydration reaction. I'll show you what that means in just a second. Okay. The triglycerides are major components of your cell membrane. Phospholipids are your fatty acids plus glycerol plus phosphate. And those are used in creating, forming cell membranes. Waxes like fatty acids, alcohols. Okay, those are cell wall of your microbacteria. And steroids. Steroids are your ring structures. Cholesterol, ergosterol, membranes of the eukaryotes, and some bacteria. Okay, so it's carbohydrates and lipids. We also have proteins and nucleic acids. Proteins are polypeptides. In other words, proteins are amino acids placed together. It's a long chain of amino acids. That's what a polypeptide is. Those are the forms of proteins. Okay, they form the long chain, and that long chain folds, like we talked about, hydrophobic, hydrophilic areas, fold that protein chain, hydrogen bonding folds that protein chain, and then it becomes active, folds in different shapes, gives you a three-dimensional structure, then it bonds together. Okay, those are polypeptides, multiple amino acids bound together. Okay, nucleic acids. Nucleic acids are your DNA, your RNA, and your ATP. Okay. DNA, the nucleic acid composed of purines and pyrimidines. Okay. Purines are your adenine and your guanine, which are one-ring structures. Pyrimidines are two-ring structures, cytosine, thymine, and uracil. So we'll talk about this in just a second, but DNA contains adenine, guanine, cytosine, and thymine. RNA replaces thymine with uracil. That's what the difference between RNA and DNA.
Professor, how do you pronounce DNA, the actual word?
Deoxyribonucleic acid.
Thank you.
Yeah, it's deoxy, because it's missing an oxygen, which showing a little bit here. Deoxyribonucleic acid. And RNA is just ribonucleic acid. Okay.
Thank you.
No problem. So carbohydrates, basic structure of carbohydrates is a sugar. Now, if you look at carbohydrate, these are your sugars. These are the aldehyde groups we talked about, the C double bond OH. And you look at all these OH groups. Okay, those are all OH groups. Those are all alcohol groups. That's what's to take sugars taste so good. Okay, that's what gives its sweet taste. You can see all the OH groups on it. And it usually exists, if you write out these chains, these are called Fisher projections. Okay, but if you draw these out, they fold over. This is how they exist in the body. They exist as these ring structures in the body. Glucose and galactose are six-pointed ring structures. There's one oxygen in there. There are 5 carbons in one. Now, fructose is a 5-member ring structure. You see the difference in shape between glucose, galactose, and fructose. And the only difference is, like between glucose and galactose, okay, is this OH group is on the right, this OH group is on the left. That's the only difference between glucose and galactose. Everything else is the same. It's just the stereo orientation of one of the OH groups, whether it's up or down from the ring. The ring structure of that same OH group is, where are we at? Down right here. It's this here. It's this. This is a hydrogen coming up here. This is an OH coming up here. The hydrogen is down. So the H and OH have switched. It's the only difference between glucose and galactose is the stereo orientation of that hydroxyl group, of that OH group. Okay, so carbohydrates. You have monosaccharides. Okay, 3 carbon. This is a monosaccharide. It's one ring structure. It's between 3 to 7 carbons. And it's the unit. And then that unit is going to be more additive. So monosaccharide is 1 unit. Disaccharides are 2 monosaccharides. And you see right here, you have 2 monosaccharides. And those join together. If you had a third one, it'd be a trisaccharide. And then after 5 or more, it becomes what's called a polysaccharide. This means multiple units. And they can be straight, they can be branched, depending on what's being formed, with this glycogen or starch. That's how the body forms fats, basically. So we use energy stores. We store extra glucose, or we store these extra monosaccharides. Right? What links them together was called the glycosidic bonds. These link the monosaccharide units together. They form the disaccharides and polysaccharides. Okay, this is a dehydration reaction or dehydration synthesis. So you have the loss of water as they polymerize. In other words, one has an OH, Not the carbon, and another has an H. Let me draw that. I'm not drawing very well here. Okay. So if we have a group that has an OH, and another group comes here with an OH, we take the OH off this one and the H off this one, and this forms water. And now this bond comes over to here. So now you have an oxygen bond between them, and you've lost water. That's a dehydration reaction, okay? Because you lose water when you form the bond. So you can see here's your H and OH. We lose an OH and an H, and then we got the oxygen left over. And that's your glycosidic bond. And that forms maltose. Maltose is glucose. It's two glucose molecules added together, it forms maltose. Okay, glucose and fructose form, glucose and fructose form sucrose. Okay, and it forms with the oxygen bond. Again, it just lost water, lost OH and H. Right? The same with forming lactose, milk sugar. Okay, you still got this oxygen. Well, here's the oxygen bond here. Here's the oxygen bond here. And you've lost an OH and you lost an H. That leaves the oxygen to make the bond between them. So the glycosidic bond is just a bond where water has been pulled off. OH from one side, H from another, and you have oxygen between them. And these are what forms your chains. Okay. So polysaccharides provide cell structure, adhesion, and metabolism. Okay. So this is, again, your monosaccharide combines with the glycosidic linkage, your disaccharide, to your polysaccharide. Okay. Lipids, those are carbohydrates, one macromolecule. These are lipids. Lipids are your fats. These are also created by dehydration. Okay. Glycerol is a 3-carbon molecule. It has 3 OH groups on it. Okay. It loses a hydrogen, and then we take the OH and we bond to that. Loses a hydrogen, loses a hydrogen. Okay. And all these are now is these carbonyl groups bonded to your oxygen. That's what we formed. Okay. If one of these attaches to glycerol, it's a monoglycerol. If 2 attach to it, it's a diglycerol. If 3 fatty acids attach to it, it's a triglyceride. This is what you measure with your triglycerides in your body. Okay. So these are all fatty acids are carboxylic acids, like we talked about just a little while ago, with long hydrocarbon chains. And there's hydrogens on all those too. But this is the end of it. So if we lose this and take a hydrogen off the glycerol, we link it to this 3-carbon molecule glycerol. And that's what forms triglycerides in the body. These are fatty acids developed in your body. We have excess fat in the body. They form the glycerol, and that's what raises your triglyceride level. When you go to the physician or the nurse practitioner and they do a triglyceride panel, okay, that's what makes your triglycerides high. Is the accumulation of fatty acids using a dehydration reaction to attach to glycerol. Okay. And that's how you form triglycerides. It's just fatty acids bonding to glycerol. Okay. So 3 fatty acids bound to glycerol is a triglyceride. Now, remember, glycerol has 3 carbons. There we go. And each one of those bonds, let me do it a little bit better here. You have 3 carbons. Each one bonds to an oxygen, C double bond O, and then to a long chain fatty acid. Monoglyceride, diglyceride, and a triglyceride. Okay. So we talked about saturated and unsaturated triglyceride. We'll talk about. Okay. Saturated means the long chain fatty acid has all single bonds. It means there's the most hydrogens possible attached. It's saturated with hydrogens. That's what saturated. We talk about polyunsaturated fats. We talk about saturated fats. Saturated means there's all carbons. Remember that these are all carbon atoms. Okay, that's saturated because everything is all bonded. If we have a double bond in there, okay, that's unsaturated, which means if we got rid of the double bond, we can put more hydrogens in there. So it's unsaturated with hydrogens. That's what saturated and unsaturated fats mean. Now, saturated fats, okay, you can see there's nothing breaking them up. There's no bonds to break them up. They're all single bonds. So you get another one that comes up to it. And these will form what's called van der Waals forces, or light forces of attraction between them. And it tends to hold them together because nothing's breaking them up. When there's a double bond in here, it changes the shape and they don't adhere as much. So saturated fats in your blood start to stack together and they form embolisms. That's what forms atherosclerotic plaque.
Isn't that when you get like high cholesterol and stuff? Like
Yep.
it clogs your arteries?
That's exactly what it, that's why it does it with this here. Okay. When they're unsaturated, it doesn't bind together and it flows through your arteries. So certain fats are good for you. Your body needs fat. I mean, avocados are a great
Like-
source of fat.
Monosaturated and polysaturated fats, right?
Right.
Are for you?
Or unsaturated, saturated, yeah. Exactly. Okay, so those are your triglycerides that are measured. Now, there's some the very low density lipoprotein triglycerides are very good for you. The high density ones are very bad for you. They're going to stick together. Okay. Phospholipids are also formed by fatty acids. They make up cell membranes, and steroids, okay, are formed. The hormones make up components of the cell membrane. Okay, so here's some fatty acids. Okay, so look at this one here. This is your acid component here. That's what's going to form with glycerol. And this is the fatty acid component. See all those hydrogen, no double bonds? This is completely saturated. You cannot add any more hydrogen bonds. It's impossible. Carbon only have 4 bonds. That is a saturated triglyceride. That will tend to stick together and form embolisms or plaque inside the body. Okay. That's palmitic acid. It's a saturated fatty acid. Linoleic acid. This is the acid part here. And you can see you have these double bonds. So theoretically, you could add more hydrogen there if you got rid of those double bonds. You could do a hydration reaction. But that's why it's called unsaturated, because there's still room to add more hydrogens. So this is an unsaturated fatty acid. These cause different bends in the molecules, and they don't line up and stick together like the saturated fatty acids. So they're a lot more healthy for it. So this is polysaturated because it has 3 double bonds. So it's what you call your polysaturated fats. And these are the ones you find in avocados, virgin olive oil, things like that are healthy fats for your body. Because you need fats to make your cell membranes. You can't go on a low-fat diet and cut out all fats. All right, phospholipids. Phospholipids are kind of cool. These are what we talked about. This is a real good example of a hydrophilic and hydrophobic component of the cell membrane. This is what makes up your cell membrane. Okay, it has a phosphate group on the top and then a tail of fatty acids attached to it. Okay, this part is hydrophilic. It has charges. It's a phosphate group, PO43 minus. Okay, this part is hydrophobic. It has no charges. Okay? This part loves water. This part hates water or fears water. This double tail. Okay? That's why soaps get your clothes clean. Soaps are made up of fatty acids. Fatty acids dissolve any stains, which are also fatty acids. And then this phosphoric head dissolves in water and it carries it off the clothes. That's how soaps work. Those are how your cell membrane works. Cell membrane is called a diphosphid layer, biphosphid layer. Okay? You have your end where you love water, okay, and your ends where you hate water. So they line up like this, with water outside and water being forced away on the inside. So here's your cell membrane right here. Okay? The hydrophilic parts are on the inside of the cell and the outside of the cell. In between the cell membrane is your hydrophobic parts, the parts that don't like water. And then force them to line up in that way and form a membrane. That's a real good example of hydrophobic and hydrophilic. So the phosphate, I guess the phospholipid is amphophilic. Amphiphatic. Okay. Does that make sense? So this whole thing, this phospholipid is amphiphatic. One part is hydrophilic, one part is hydrophobic.
Yes.
Okay, and that's how they line up to form your cell membrane. Because there's water inside the cell, water outside the cell, and the cell membrane, the hydrophobic part, helps keep this membrane all intact. Okay. This is an example of cholesterol. Here's your biphospholipid, their phospholipid bilayer. So you got your phosphate heads here, phosphates heads here. Okay, so this is all hydrophilic. Hydrophobic is inside it. So cholesterol, which is hydrophobic, comes in here and wedges inside the membrane and allows proteins to be in the membrane, and it allows certain channels for things to pass through along with the cholesterol from the outside environment to the inside and from the inside to the outside. You have to pass, like oxygen, it has to pass from outside the cell to inside the cell, so we can use it for metabolism. Carbon dioxide builds up, has to pass from the inside of the cell to the outside of the cell. It has waste products. But cholesterol embeds in the cell membrane. It helps provide support for it and for the passage of different materials through that cell membrane. All right, so triglycerides that have double bonds in the fatty acids are best described as saturated, unsaturated, phospholipids, or cholesterol.
Unsaturated.
They would be unsaturated. You got it, perfect. Because they still have space to add hydrogen to them from that double bond. Proteins, so we covered carbohydrates, lipids, and everything with proteins. Proteins make up all the enzymes and all the parts of your body. Okay? They're made up of amino acids. That's the unit. There's 20 different amino acids in your body. Every single protein in your body, enzymes, everything that we use to function with, is made up from those 20 amino acids. And they're linked together in a specific order. How they get that order is from your DNA. Goes to DNA, goes to messenger RNA. It transcribes it. In other words, there's an amino acid sequence in your DNA. It opens that chain up and it reads that sequence. It puts in this messenger RNA. This goes out of the nucleus into the cell and attaches to a ribosome. It attaches to this ribosome. And it's like a little printing press, and it stamps different trions with different tricodes on it, with 3 at a time. Okay? Each tricode codes for a specific amino acid. And these amino acids are linked together. Every amino acid has the exact same structure except for the R group. So every single amino acid is going to have a hydrogen, nitrogen, hydrogen, bonded to carbon, bonded to hydrogen, bonded to carboxylic acid. Okay, and we link here, and we link here. We can form links from both ends of it. And then this carbon here, this R group is the only difference. Every amino acid has that exact same structure you're looking at, except for the R group. And this is the R group for a protein called alanine. Alanine has a CH3 group attached. Okay, valine has this carbon group attached to it. Every amino acid is the exact same chain that's going to link, except for what hangs down in that R group. Those are the only differences. And that's what determines all the proteins in your entire body, 20 of those. Okay, so cysteine has a sulfur group in it, CH2SH. Okay. Phenylalanine had this is what's called a benzene ring. Okay. It's a 6 carbon with alternating double bonds, has special properties. So that's phenylalanine. Okay. If you ever have a patient that has PKU, phenylketonuria, they can't have proteins that have phenylalanine in it. They can't break. The phenylalanine builds up in the body and causes a toxic reaction. It causes mental retardation and eventually death. But it can be controlled by diet. You don't give them food supplies, food sources that has the amino acid phenylalanine in it. And that's called PKU, phenylketonuria. It's a genetic disease. They cannot break this structure down right here, and it builds up and becomes toxic. Tyrosine. Okay. One of the amino acids is also called tryptophan. Tryptophan is the precursor to melatonin. What does melatonin do?
Puts you to sleep.
Puts you to sleep. You know what has the most tryptophan in it? It's turkey. Turkey has huge amounts of tryptophan, which explains why. What happens after Thanksgiving dinner? What do?
You get tired.
Tired.
Yeah. You sit down, you watch football, and you go to sleep. That's what everybody is. Because turkey has the amino acid tryptophan, and tryptophan turns into melatonin. So you just dose yourself with melatonin and you're going to go to sleep. So that's why you feel tired after Thanksgiving dinner. So amino acids attach what are called peptide bond. These different amino acids attach to each other, and they always attach the nitrogen carbon group, nitrogen carbon group, nitrogen carbon group. Okay? And they continue to attach to that end, and they build into a chain. And the R group, like I said, the R group is the only difference. I'm coming up here, down here, up here. Okay? That's the only difference. That whole chain of all proteins, exact same chain, that backbone, and the R group hanging off is different. That's what's going to turn all the difference in your protein. Okay? And every one of those is a dehydration reaction. You're releasing water, releasing OH and H. And that forms water. Water is very stable, and that carbon-nitrogen bond forms. And these are called peptide bonds that bond amino acids together. Okay. Proteins fold into very specific three-dimensional shapes. Your whole body works by shapes. Everything revolves into shapes of receptor of how we respond to something. How your cells respond to insulin is about how it bonds to it. How you respond to THC, marijuana, binds to certain proteins. How you respond to adrenaline. It all bonds to shapes of receptors on the cells. All right, so these proteins function to support. They build your body. They make your body a structure so you can stand up without becoming just a blob or a mess. They give you support. They form enzymes, which break down all the food for you. They transport different things from different parts of the body. Defense mechanism against pathogens that invade your body. Allow movement, creation of ATP. Okay. There's 4 structural parts of a protein. There's primary, secondary, tertiary, and quaternary. So you have a primary portion, you have a secondary portion, you have a tertiary portion, and you have a quaternary portion. Okay, those are your levels of development of a protein. Okay, primary comes first, then secondary, then tertiary, then quaternary. So primary structure is strictly the line of amino acids linked together. So it's amino acid, all linked together in line. That's your primary structure. The order of the amino acids. Okay. Secondary structure, these start to fold. They'll form 2 types of structure. They'll form what's called an alpha helix, which is a single strung rung of a ladder being formed in shape, or beta pleated sheets. Okay, those are the 2 structures they'll form. They'll form an alpha helix or beta pleated sheets. That's your secondary structure. So you have your line, then they start to form into either, like picture a ladder, just bend one end of it. That's your alpha helix or beta pleated sheets. The next one is your tertiary structure. The tertiary structure is when those alpha helixes or beta pleated sheets start to form a 3-dimensional structure. Okay, so these tertiary ones form a 3-dimensional structure, and they start to fold depending on the hydrophobic and hydrophilic. The hydrophilic regions are going to fold out where they're exposed to water. The hydrophobic portion are going to fold in where they don't react with water because they're not polar. Okay, that's your final 3-dimensional shape. Now, certain proteins require more than one protein to work. Hemoglobin. Hemoglobin requires 4. Hemoglobin for red blood cells requires 4 chains to link together. That's your quaternary structure. That's the 4th step, is when these 3-dimensional chains link together to form an overall one, where you get ones with more than one polypeptide chain. Okay, linked together. Okay. So we got primary is just the line, amino acid of the order. Secondary is when they start to form alpha helices or beta pleated sheets. Tertiary is when they form their final three-dimensional structure. And quaternary is when these molecules that have been formed link together to form a massive unit or a large protein, something that can be biologically active. They become one. Okay, so here's your primary structure. This is just your line, right? Here's your secondary structure. They start to form this alpha helix, or they'll form a beta pleated sheet on this side. And then they form a three-dimensional structure. Okay, then more than one of them come together to form the quaternary structure, the overall active structure. Now, some are active right here. Some only have the one, they have one strand, they form the three-dimensional structure, and they go off and they do their thing. I think insulin's that way. Insulin's just a single strand, single amino acid strand. Okay, but a lot of the other ones are quaternary, where they come together and form more than one of these units that are formed. Does that make sense?
The quaternary one, it says right there, a structure of BRCA1 human tumor. So they become more of like a four-dimensional mass, or
No. They're still three-dimensional. They're just more than one chain. In other words, you had another one that went through, another one had primary, secondary, and tertiary, and these two now got together. And another one that went through primary, secondary, tertiary, and then they got together. This forms your quaternary structure. It's not a different thing. It's the same ones, but they're different proteins that have come together to form a unit.
got it. But that's a tumor right there.
I'm going to get some protein that consists of organ the structure. Human tumor. No, this is a protein that suppresses tumor. This is a protein that destroys tumors. It's a BRCA human tumor suppressor protein. So this structure right here, it has at least 10 different pipets that I can see. This is one that goes around and searches tumors in the brain and destroys them. Okay.
Thank you.
Yeah, your body won't build tumors. Okay, tumors are abnormalities in the body. That's from an acceleration of the growth cells of your own body cells. But they will make proteins that will find this defective growth and destroy it so it doesn't multiply and spread through your body. Does that make sense?
Yes. So when your body lacks those proteins that can find that and destroy it, then that's when they grow and develop. Like
Perfect. Very good. That's a really good point. That's a great point. A lot of times, that's why they can do genetic coding for different types of cancer. Because if you're missing a certain enzyme, like that prevent breast tumors from forming, breast carcinoma from forming, then you have higher incidence of breast cancer. And that's what they do these tests on. They test to see if you're producing those tumor suppressing proteins.
got it. Thank you.
Now, I think it was Angelina Jolie that was going to have 2 mastectomies because her numbers were, she wasn't producing the tumor suppressing proteins. That's one of the famous celebrity cases. I don't know if you got it done or not, but that's what they check for. They check for these suppressor proteins. There's all kinds of neat ways that the human body works, and you got to realize cancer, the big problem with cancers are why we can't fight it. It's our own cells. Cancer is our own cells just multiplying at a rapid rate, producing a large mass. Okay? So how can we kill something without killing our own cells? And that's what chemotherapy is. Chemotherapy is a race to see who wins first. We're killing the human cells, but we try to kill the tumor cells first. Okay, but if we don't, the patient dies. But that's why chemotherapy is a nasty treatment, because it makes you sick, your hair gets, all kinds of stuff, because you're killing human cells. Because cancer cells are just our regular cells. We have no magic bullet to only isolate those. Okay? And we got all kinds of proteins, all kinds of enzymes that are released into the bloodstream. We got like NK cells, natural killer cells. These cells go through your body, maybe look for cancer cells, and they kill them. And we don't know how these little guys, these NK cells, can find, like B cells and T cells, these NK cells, they can find certain tumor cells, certain proteins in tumor, and we don't know the difference, but it does, and it destroys tumor cells. There's all kinds of neat stuff that as you learn about the body. It's phenomenal. All right, so we talked about carbohydrates, lipids, proteins. Last one is nucleic acids. This is your DNA, RNA, and your ATP. Oh, here's it spelled a lot better. This is a lot neater than I can write. Deoxyribonucleic acid. If you want to look for the spelling of that, because my writing is not the neatest. I know that. So DNA and RNA are nucleotides. Okay, DNA is deoxyribonucleic acid. RNA is ribonucleic acid. DNA has adenine, thymine, cytosine, and guanine as your bases that combine to form the cross bridges. Adenine binds to thymine, cytosine binds to guanine, and that holds these two ring structures together because DNA is a double helix. There's two helixes. It's like taking a ladder and twisting the ladder. Those form your two helixes around it. And the rings in between there are the bases that connect. So adenine again to thymine, thymine to adenine, and so on. But adenine is always paired with thymine, cytosine always paired with guanine, and vice versa. These are nitrogenous bases. It forms, like I said, a double helix, and this is your hereditary material. This is what's passed on from generation to generation and allows people to evolve with different environmental stimuli. Ribonucleic acid. Ribonucleic acid is similar, except it is single-stranded. It is not a double helix. It's one strand, and it does not have thymine. It replaces thymine with uracil. So RNA uses, so adenine bonds with uracil, cytosine bonds with guanine in RNA. The RNA is used for protein synthesis. RNA reads the genetic information from DNA, travels outside the cell nucleus into the cytoplasm where the endoplasmic reticulum is with the ribosomes, binds those ribosomes, and then it decodes that material into forming a protein chain, your primary structure. That's how it works in a nutshell. But this is it, it's a sugar phosphate background. You have a sugar phosphate, sugar phosphate, sugar phosphate, and it builds this background. And this is your nitrogenous base, adenine, guanine, cytosine, and thymine, pages of DNA. These all contain nitrogen. Okay? So these nucleotides are a phosphate, a 5-ring sugar, and then your nitrogenous base. And these, like I said, the sugar and the phosphate form the backbone. And then the rings of the ladder connect out here. These are your bases, adenine, and connect to another one. And then this is a sugar phosphate backbone. So it's either going to be adenine, thymine, guanine, or cytosine. That's in DNA. And RNA, we use uracil, and there is no uracil takes the place of thymine in RNA. Okay, and that's what it looks like. There's your sugar phosphate background right here. Sugar phosphate backbone going down on both sides. Okay, and then cytosine pairs with guanine, adenine pairs with thymine, guanine pairs with cytosine, thymine pairs with adenine pairs with thymine, cytosine pairs with guanine. And these are hydrogen bonds, which you talked about. Hydrogen bonds is what holds your DNA together. Because remember, you got to unzip this. You got to break these bonds to make it work. You got to take your DNA and open it up. You have to unzip. Hydrogen bonds are weaker bonds than covalent bonds or ionic bonds, right? They're weaker bonds, they can be broken. So you can open those up. Once you open those up, you expose this area for an RNA to come and bond to it. That's what's called a gene. Okay, those are your genes. That's what supports the RNA to bind to it and take that genetic information and move it into making a protein in the cell. So in DNA, the polymer is composed of alternating deoxyribose and the phosphate with nitrogenous bases. Okay. DNA is almost always is a pair of strands. They're a single when they open up for replication or for translation into a protein. Okay. This is RNA. Remember, RNA is single-stranded. So all you've got is out here. And remember, there's no thymine, it's uracil replaces it. So uracil, adenine, cytosine, guanine, cytosine, adenine. Okay. It's single-stranded and it has uracil instead of thymine. Okay, so deoxyribose Deoxyribose means it's missing an oxygen at the number 5 position. We'll show that in just some pictures here too. Cytosine, guanine, thymine. The sugar is deoxyribose for DNA and it's ribose for RNA. And again, you have uracil instead of thymine. Okay, so here's your deoxy, here's your ribose. Now look at the difference. Let's look at, let's pick the color you can see. You can probably see, well, you can see purple pretty good. All right, so right here. Okay, and right, I can't see that one, maybe see this one, but there we go. Okay, that's the same position, right? It's 2 carbons away from the oxygen. In the ribose, there's an OH group. In the deoxyribose, the OH is missing. You're missing an oxygen. So deoxy, no oxygen at that one point. Okay. So the number 4 carbon is missing a oxygen. It's deoxyribose. The other one is ribose. That's where you get the name from. Does that make sense?
Yes.
Okay, perfect. That's why I have DNA and RNA, deoxyribose and RNA, different sugars. And then the bases, you have purines and pyrimidines. Your purines are adenine and guanine. Okay, those are your double ring structures. And your pyrimidines are thymine, cytosine, and uracil. Those are your single ring structures for nucleic acids. So DNA is a double helix. It's like taking a ladder and twisting it on the inside with all the rungs being these strands and all these connected between them to hold the structure together. And they're all linked by hydrogen bonding between these nitrogen bases. Like I said, if you have adenine there, then it's compared with thymine. If you have guanine, it's compared with cytosine. Okay. So in replication, okay, when cells multiply, you have to make sure the DNA gets replicated. It opens up and copies each strand, forming a daughter cell with the exact same DNA as what you're copying. So each strand is copied. Okay, replication is guided by your base pairing. Adenine pairs back with thymine, guanine pairs with cytosine, and vice versa. So as you open those up and you make 2 new strands around those openings, you end up with 2 new separate double strands that are identical to the original parents. This passes your genetic information on from one parent to the next cell, onto their sibling.
Is that how they do like forensic like testing, like when they're trying to get someone's DNA off of certain things? Because it
yeah, definitely you match the DNA sequencing. Now, all the DNA sequencing that pairs for certain proteins are going to be the same for every person in the world. I mean, the gene that pairs for insulin is the same one for you, me, everybody. Okay? It's going to make insulin, or it's going to make, I'm thinking of something else the body makes, cholesterol. Okay, that gene is going to be the same. It's the non-producing portion of the DNA that they use for forensics. And that's like 99% of it. 90% of the DNA, we have no idea what it codes for. That's where everybody's different. So we take those pairs and we can match those strands. And if you have exact matches to those strands, you can have a 99.999% chance of that's the person to match that DNA to it. That's what they do. They use the non-coding portions of the DNA, which is just the random portions. And if that random portion matches that random portion, it's a match. And you can do similar ones for people that are related and so on and so on. But that's exactly how they do it for forensics. I think we have a lab on matching genetic material too, which is really interesting. Okay, but that's how we do it. That's how forensics does it. Okay, so this is how they replicate. This is your DNA. Your DNA unzips, opens up, and then new nucleic acids come in there and bond to it. And it forms another strand. And this strand are the exact same thing as that strand. And then this goes to this cell, this goes to that cell. So each cell now has an exact duplicate of the original DNA that started with. So when cells multiply, they keep their DNA. Okay. ATP, any questions on DNA?
No.
All right, perfect. All right, DNA is adenosine triphosphate. It's an adenine purine right here. We have the sugar group, and then we add phosphates to it, PO4 groups. If we add one group here, it's adenine monophosphate. If we have two groups, it's adenine diphosphate. If we have three groups, it's adenine triphosphate. Adenine triphosphate has a high energy bond right here. When you break that bond, energy is released. That energy is used for muscle contractions, anything that need energy in the body, that's what it's made for. ATP stores energy that we can use by breaking that high energy phosphate bond and produce energy where we need it. Okay? There's two things muscles have to contract. Remember, your heart's a muscle. A muscle has to have calcium and it has to have ATP. Those two things are necessary for all muscles to contract. Okay? So you have to have those. ATP is your energy storage for the body. It transfers energy so things can happen. It's in the form of ATP. Okay. Which of the following is true about RNA? Is A true? Is it a double-stranded molecule? No, it's single-stranded, right? DNA is double-stranded. It contains the sugar deoxyribose.
C? Is it C?
Is it, if nitric base contains uracil? Yeah. It holds genetic information, it transmits it. It is C. Contains uracil. Remember, uracil replaces thymine in RNA. It's single-stranded. It contains ribose as its sugar. And it's a recording of the genetic information. It doesn't hold genetic information. It records it and sends it into the cell. So it would be C. Contains nitrogenous-based uracil.